Alrighty, folks, so we'll move on here to Chapter 1, Lesson 4. We're going to be taking a look at some kinematics formulas in this lesson. Just a reminder, okay, make sure you are following along with the notes, actively engaging. If that means printing out and following along, that's great. I'd probably recommend that, but you can also just follow along on loose leaf, but we want to make sure we're actively participating and taking notes, not just sitting back and watching the video. All right, here we go. So we're just going to start out by reminding ourselves about acceleration, because that's going to come up a lot today as we are analyzing non-uniform motion algebraically with these formulas, okay? So reminder, all acceleration is the rate at which an object's velocity is changing, okay? So how much is its velocity in meters per second changing by each second? And so that means if an object is speeding up, slowing down, or changing directions, it is accelerating. Because remember, velocity has both a magnitude and a direction. So if the direction changes, that's still an acceleration because it's still a change in velocity. So an acceleration in meters per second, or meters per second squared tells us how about an object's velocity is changing each second. And remember, we looked at this a lot in the previous lesson. If something is speeding up, well, that just means its velocity and its acceleration are in the same direction, right? So it gets faster. Maybe it's got a positive velocity and a positive acceleration, so that velocity just gets bigger and bigger in the positive direction, right? Or negative velocity, negative acceleration, it gets faster and faster in the negative direction. And remember, it is possible for an object to be moving in one direction but accelerating in the opposite direction. That just means it's slowing down, it's getting slower. So if the object's velocity and the acceleration are in opposite direction, the objects get slower, right? Maybe it has a positive velocity and a negative acceleration. So it is moving in the positive direction, but its velocity is changing towards the negatives, right? And so that just means it's getting slower and slower and slower. Okay, special note, we sometimes refer to that as a deceleration. Remember, it is still an acceleration. A deceleration is still an acceleration. It's just a special type where the change in velocity results in the object moving slower. It's just being a bit more specific, but it's still an acceleration. So I know we did this in the previous lesson, but we're going to do it again to just remind ourselves and really get a feeling for and be comfortable with what an acceleration really represents, because sometimes it's a concept that trips students up a bit. Okay, so we're going to complete this table for some object that is initially moving forwards at 2 meters per second. So its velocity when we start out is 2 meters per second forwards. However, it is accelerating backwards at 1 meter per second each second, or 1 meter per second squared. And it does that acceleration for 4 seconds. So that means we have this scenario, right? If I call forwards positive and opposite directions need opposite signs, so backwards will be negative, right? That just means our initial velocity is positive 2 meters per second, but it's changing by negative 1 meter per second each second, right? The acceleration is negative 1 meters per second squared. So all that means is if it starts out going at 2 meters per second, after 1 second, it will have changed by negative 1 to become positive 1 meter per second, right? Now notice, still positive, so it is still moving forwards, but it's gotten slower, right? It changed by negative 1. So it changed towards the negatives. Still positive, but it's headed towards the negatives because it's changing by negative 1 meter per second each second. So notice, after 2 seconds, it actually does briefly come to a stop. Right? It momentarily is not moving. We explored that a lot in the previous lesson, okay? But now it's going to continue accelerating. It says it does this acceleration for 4 seconds. So in the next second, what will its new velocity be? Negative 1 meters per second. So what's actually happened now? It's actually started moving in the negative direction. So if we want to picture this, it was moving forward, but getting slower, stops, and now starts moving backwards, okay? And after another second, it's going to be going negative 2 meters per second. So we can see it's now actually getting faster in the negative direction, right? The next second, if it continues, it would be negative 3, and then negative 4, negative 5 meters per second. And so notice in this short little scenario here, we actually see both of these concepts in action, right? At first, it was moving forwards, so its velocity was positive, but the whole time it's accelerating backwards. So we'd say its acceleration is negative based on how we define them, right? And so what did it do? What happened to its speed when this was the situation? It got slower, right? It was started out moving forwards at 2 meters per second, then only moving forward at 1 meter per second, briefly came to a stop, okay? But then once it actually turned around and started moving backwards, so now its velocity is backwards, but its acceleration is still backwards like it's been the whole time, then what happened to its speed? Well, yeah, now it's getting faster and faster. It's just going in the negative direction, right? So the acceleration and velocity are kind of working together here, so it gets faster in the negative direction. Here, the acceleration's like it's working against the velocity, right? Positive velocity, but negative acceleration for the green section there. Okay, so just, again, a reminder, a refresher on what an acceleration really means, because that's important to have a solid understanding of as we head into algebraic analysis here. All right, so in the previous lesson, we looked at non-uniform motion a lot, but all of our analysis was graphical, right? We weren't really using formulas and manipulating and plugging in numbers. We were looking at graphs. It's a good way to introduce the concept, but another tool in our kit, another way we can work with this, is algebraically analyzing non-uniform motion using our kinematics formulas, okay? So that is what we are going to do today. Now, throughout the lesson today, there are 5 formulas we're going to use, okay? 4 of them are new. They're actually the first thing you've done in Physics 20 that you had not seen in Science 10. So after today, we are officially into Physics 20 and out of our kind of Science 10 review, so to speak, okay? So don't panic. Oh, 5 new formulas. I know it sounds kind of scary, but it's actually just because there are 5 main quantities we might be interested in when doing kinematics, the study of objects moving, right? So those 5, you've seen them before, are displacement, initial velocity, final velocity, acceleration, and time, right? So how far did the object go from where it started and in which direction? How fast was the object moving at the beginning and in which direction? How fast was the object moving at the end and in which direction? How much was the object's velocity changing by each second and which direction was it changing? And finally, time, right? How long was the object actually moving? So those are kind of the 5 things we might use to describe or look at an object that is moving with non-uniform motion, okay? And so the reason there are 5 formulas is that each of them is just for when you don't know and don't care about finding one of those variables, right? So there's one for when you don't know and don't care about displacement, one for when you don't know, don't care about initial velocity, et cetera, et cetera. So we're going to look at those 5 different equations today, okay? But that's kind of the intro overview thing of what we're doing here. Each of the 5 equations we're going to learn are for when a variable doesn't appear in that equation, and therefore we want that because we don't know it, but we also don't care about finding it, so we don't need it to be in our equation, okay? Just a side note here, you might be saying, okay, great, these are for for non-uniform motion. What about for uniform motion? Well, for uniform motion, we can just use good old v equals d over t, right? It's uniform, its velocity is not changing, so it is always covering the same displacement each second, okay? For non-uniform motion, remember, you cannot use v equals d over t. It just doesn't make sense because it's not covering the same displacement each second. Its velocity is constantly changing, so the displacement it's covering each second is constantly changing. A good way to really see why this doesn't make any sense if the object is accelerating is to rearrange it for displacement, right? If an object is going 10 meters per second constantly for 10 seconds, right? We could say, okay, well, it goes 10 meters each second times 10 seconds to figure out how far it goes. But that goes out the window as soon as the velocity is changing, right? For 1, what's the velocity? It has many different velocities, right? For 2, if we say, okay, it starts out not moving and speeds up to 10 meters per second, and it takes 10 seconds to do that, well, we can't just do 10 meters per second times 10 seconds then, because for most of that time, it wasn't moving 10 meters each second, right? For most of that time, it was going slower, okay? So just a word of warning, because sometimes students do try to use this equation for non-uniform motion. It does not make sense, okay? It doesn't work unless what you're interested in is the average velocity, but most of the time we're not. We're interested in actually finding a specific variable. Okay, before we jump into the equations, let's just get some special things to keep in mind out of the way, because they will pop up in a lot of these questions. So often we'll see questions where something is dropped, right? An object is falling towards the ground, okay? A very common student mistake here is to say that, okay, so it's gonna hit the ground and then it will stop, so the final velocity is 0, okay? But that's not what we're actually analyzing. We're analyzing the fall. So its final velocity is at the end of the fall, which is the instant right before it hits the ground, right? Once it hits the ground, we're not analyzing the fall anymore, right? We're analyzing the impact. Once it hits the ground, there's a new force involved, that impact force, which we'll talk about in Unit B, and therefore there's like new accelerations, right? Forces cause acceleration, so once it hits the ground, we now don't know what our acceleration is, and it has nothing to do necessarily with the fall on the way down, right? So our final velocity whenever an object is dropped is not 0. It's the velocity right before it hits the ground. And the next kind of special consideration here are things you got to know. Well, you don't have to know it, it's on your formula sheet, but acceleration due to gravity, so whenever something's falling, as long as it's on Earth, which unless they say otherwise, we can assume it is, acceleration on Earth due to gravity is 9.81 meters per second squared downwards, okay? So anytime you need to solve a problem where something is falling, that's the acceleration you're going to need to use, okay? As it appears on the back of your formula sheet, you can see here, right? So it's given to you as 9.81 meters per second squared. That's what you should use. Anytime an object is at rest, okay, its velocity is 0 or comes to a stop, right? That's what those mean. So if it starts at rest or if it ends at rest, okay, that tells us VI or VF is 0. Any object that is dropped, okay, where we say we drop something, we know that means its initial velocity is also 0. Because when you drop something, right, if you drop a ball, at first it's not moving, okay? 1 nanosecond later it will be because it's accelerating downwards, right? But at first it's not moving, okay? Every second its velocity will change by 9.81 meters per second in the downward direction. So, 1 second later it'll be moving at 9.81 meters per second down. 2 seconds later it'll be moving at twice as fast down, okay? But at first it's not moving for any object that is dropped, okay? And as always, but good to get a little reminder in now, remember you always need to consider the direction and therefore the sign of vector quantities that describe an object's motion. If they're in the same direction, they must get the same sign. If they're in the opposite direction, they must get the opposite sign. So if your velocity is forwards, but your acceleration is backwards, for example, you will get the wrong answer if you make those both positive. You need to give them opposite signs because they're in opposite directions. Okay, let's jump in. Exciting stuff. So the first of our 5 kinematics equations for non-uniform motion is actually review. It's the one you already know from Science 10, okay? And so that just tells us that the acceleration is equal to the change in velocity divided by the change in time. Remember, to find a change in anything, you can do its final value minus its initial value, right? I mean, how long has it been since you were 10 years old? You can probably do that math now in your head, right? And what did you do? You took your age now and you subtracted 10 years old, right? Where you ended up minus where we're interested in you starting. And that tells you the change in that quantity, okay? So written out a little more explicitly, the acceleration is equal to final velocity minus initial velocity, that's just the change in velocity, divided by the change in time. So on our formula sheet, we can see that one here. Notice they don't put the VF minus VI in, they just say change in velocity, but you know that change in anything is just final minus initial. Just as a bit of a spoiler, here are the 5 kinematics equations we're going to be looking at today. So we've introduced ourselves to 1, 4 more to go after we explore this one a little bit more. All right, so as I said earlier, right, each of the 5 kinematics formulas we're going to learn today are set up so that they can be used for not knowing and not caring about one of these variables. So which of these variables do you think that is for this equation? Well, which one doesn't appear, right? Here's our 5 kinematics variables. Displacement does not appear. So we can use this formula when we don't know and don't want to know the displacement. right? And we can see that that's good because if I don't know the displacement, well, I'm not going to have to know it because I don't have to plug it in anywhere in this equation. But if I wanted to know the displacement, this equation's no good because it doesn't have displacement in it, right? I can't solve this for displacement. Displacement's not there. Okay, so in this lesson, we're going to get a lot of practice with the skill of manipulating an equation, a crucial skill in physics, okay, and in a lot of courses. Now, you already have the core skill set from math, but we're going to really use this lesson as an opportunity to workshop that skill, okay? So every time we learn a new equation today, we're going to right away manipulate it, mess around with it, get comfortable with that process. So it's asking us to isolate final velocity in this equation, okay? So first things first, always just identify what variable you're trying to isolate, okay? And next, we always ask ourselves, okay, we want to get this alone, right? Why is it not alone? Because operations are being performed on it. It's having VI subtracted from it, and then all of that is being divided by time, right? And so now we need to undo those operations. To undo operations, we do the opposite operation, and we need to do it to both sides, okay? So that's the core idea here. Undo whatever's happening to final velocity until it's all by itself, okay? Now, since we're undoing those operations, we need to follow the reverse order of operations, right? So not BEDMAS, but SAM-DEB. Okay, so we need to make sure we're undoing the operations, but we're following the correct order here. Okay, so that means we have to deal with subtractions and additions before we can deal with multiplications and divisions, before we can deal with exponents, and all of that has to be dealt with before we move inside any brackets. Now that bracket thing becomes important here, because even though, you know, they're not necessarily always written in, because we're dividing multiple things here, an operation by time, everything up here is being divided by time, there are what we call implied brackets, right? You can notice that putting in those brackets doesn't change what I'm doing here, right? So those brackets are part of it. So we actually need to, before we can get into those brackets and start working on, you know, final velocity, or this subtraction, I should say, we actually first need to get rid of this division by time. So final velocity, yes, it's having VI subtracted from it, but that's happening inside brackets. So first, we need to deal with the fact that it's being divided by time. What's the opposite of being divided by time? Being multiplied by time. So if I multiply both sides by time, we see it cancels out here, right? And I'm left with this now, right? I'm just going to actually put in the brackets so we can see that there, right? So now we have time times acceleration is equal to velocity final minus velocity initial, okay? I dealt with the multiplication division, and now I've dealt with everything outside of the brackets, right? So once I've dealt with everything outside of the brackets, I'm good to get rid of them, and we just repeat this process. We ask ourselves, okay, I want to get final velocity by itself. What operations are being performed on it so that it's not by itself? Well, it's having VI subtracted from it. So what's the opposite of subtracting VI? Right, it's adding VI. So if I do that to both sides, minus VI and plus VI are going to cancel out on that side. And on the left, I'm going to have T times acceleration plus the initial velocity should equal velocity final. And we just keep asking ourselves, okay, is velocity final now by itself? It is. We isolated it, right? We did it. So it's common practice to usually write the isolated variable on the left side, though we've technically done it here. We are good to go. I'm just going to rewrite it, though, as the final velocity is equal to the acceleration times the time plus the initial velocity. Okay, and there we go. This actually makes a lot of sense when we think about it too, right? How fast were you going to start with plus how much your velocity was changing each second times how long it was changing that way, right? This overall gives us the total change in velocity because it's how your velocity was changing each second times the number of seconds it changed for. So if you add the change in velocity to where your velocity started, you'll end up with your final velocity. Okay, so there we go. Let's try solving for VI now. It's the same process every single time, okay? We're just isolating a different variable now. So we always kind of work outer to inner, so to speak, right? It's almost like packing a suitcase and then unpacking a suitcase. You kind of have to unpack the outer stuff to get into the inner stuff. So if we take a look here, the acceleration is equal to velocity final minus VI over time. We want to isolate VI now, okay? But again, we know this is all in brackets, right? Everything is being divided by time, so there's implied brackets there. So before I deal with anything inside the brackets, I need to deal with everything outside of the brackets. So everything is being divided by time. Let's multiply both sides by time. That gets me here, okay? And now I gotta be careful, right? But I want to solve for VI. Right now, VI is being subtracted from VF. So there's a couple ways I could go here. I could add VI to both sides to just make it positive, right? Or I could subtract VF from both sides, but I have to remember that I'll still be left with a negative VI, right? That minus doesn't go away just because I subtract VF. So I'm going to choose here, I'm going to add VI to both sides, okay? I'm going to add VI to both sides, and that way I know I've made it positive. I don't have to worry about that negative. It's okay if you get the negative VI isolated. You would then just divide everything by -1 afterwards. So if I add VI to both sides, I get to this stage where now TA plus VI equals VF, okay? But always, right, just take a breath and then ask yourself, what's next? I'm still trying to get VI by itself. It's not by itself. Why? Because we're adding TA to it, right? So I need to undo that. I need to do the opposite of adding TA to both sides. The opposite of adding TA is subtracting TA. And so just moving up here where I have a little more room, that's going to leave me with the initial velocity is equal to the final velocity minus times acceleration. Or we could do acceleration times time, right? And there we go. Now we've done it. Initial velocity is by itself. So notice, exact same thought process always. What do I want to isolate? Why is it not isolated? What operations are being performed on it, right? What's the opposite of that operation? And do it to both sides, one step at a time until you've got it by itself. Okay, last one here for this equation. We got to isolate time. So now everything is being divided by time. Right? I am never going to solve for time while it's down here in the denominator. So let's just get time out of the denominator as our first step, and then we can work on isolating it. Okay? So still the same process. I don't have time. Why? Because time is dividing everything on the right side. So what's the opposite of dividing by time? Multiplying by time. And we get this, okay? So now we pause, we take a breath, and we ask ourselves, okay, I want to get time by itself. It's not by itself. Why? Because it's being multiplied by acceleration. So I need to undo that. What is the opposite of multiplying by acceleration? It is dividing by acceleration. So if I do that, acceleration over acceleration is just 1, and I'm left with the time is equal to final velocity minus initial velocity divided by acceleration. Okay, let's actually solve some problems. But before we do jump into analyzing some problems with our formulas, okay, let's just quickly go over the general kind of thought process, the problem-solving process for any physics problem, or really any, problem, okay? First things first, we're going to want to draw a diagram, okay? I know especially at first it might seem a little bit annoying, like you could just put the numbers in and get your answer, okay? But I promise there will be times where drawing a diagram might help you understand the situation a lot clearer. It might let you catch something you might have missed. Maybe you missed that the velocities were actually in opposite directions, final and initial, from before you drew the diagram, those types of things, okay? And I promise where we're headed, you're eventually going to absolutely need a diagram to solve a problem, so it's a good habit to get into now early, okay? And then we get into actually dealing with our numbers, okay? So we're always going to state our given variable and our required variable, because that's going to let us choose the equation that will let us analyze, okay? Before we move on to that, though, we want to make sure all of our givens are in standard units, so that's meters, seconds, and eventually kilograms later in the course, okay? So that means not kilometers, meters, not hours, seconds, right? Not kilometers per hour, meters per second, okay? So we'll have to do conversions if necessary, okay? Sometimes we can get away with it if our units all work together. Most of the time, we'll just want to get them into standard units, okay? So once we've chosen the correct equation from our formula sheet, okay, which will be the equation that has the given variables or variables we know and the variable we want to know, right? We take that equation, we write it down from our formula sheet, and then if necessary, we manipulate it just like we've been doing. So we use opposite operations, right, to undo the things being done to the variable we want to isolate, following that reverse order of operations to solve for what we need. Finally, we can then plug in our numbers. If we've gotten this far, as long as we don't make a mistake on the calculator, we should be good to go. Okay, so we'll plug in our numbers and we'll solve. Now that we're actually performing the operations, we're going to follow the regular order of operations, BEDMAS, okay? And then the last step is really just take a second, pause, make sure you've actually answered the question, right? Was it just to find the number, or was it to say something about that number, right? Was she speeding? Those types of questions, okay? Do all the checks. Do you have the right number of sig digs in your final answer? Do you have your proper units? And if it's a vector and you can state the direction, have you stated the direction? Okay, so we sometimes call this the GRASP kind of process, right? And that just stands for givens, required, right? What are you given? What are you asked to find? Analysis is choosing the formula and manipulating it. Solution is just plugging in the numbers and calculating. And then paraphrase kind of lumps in all of those checks, right? Do I have sig digs? Do I have units? Do I need to give a direction? And have I actually answered the question? So notice how much of this process is really kind of set up and just, making sure you're carefully thinking about what you have and what you want to find, right? It's not so much about calculating, it's about identifying the variables you have, the variable you want to find, and which formulas are going to let you get there. Okay, so with that in mind, let's go ahead and apply this in our first example. So a new scooter can accelerate from rest to 60 kilometers per hour in 6.13 seconds. Okay, so a lot of things we just learned. From rest, the initial velocity is 0, right? From rest to 60 kilometers per hour. Now, we want to have an alarm set in our head. We know we're probably going to need to convert that, right? We're going to need that in meters per second, okay? But that's the velocity it ends up with, so that's its final velocity in 6.13 seconds. So that's time. So I'm just going to make a little list, right? I'm going to do my givens. What am I given? So there's all of the variables I already know the value of. Now, again, kilometers per hour, we are going to want meters per second, right? First of all, this is in seconds, so that won't work well with hours. Finally, we want an acceleration. That's always going to be in meters per second squared, right? You're never going to see that in kilometers per hour squared. Typically, once we move on past uniform motion, we're always just going to be in meters and seconds. So a little reminder of how to convert this, right? We've done it before, but let's remind ourselves. We need a conversion factor. We have two things to take care of. We don't want kilometers, we want meters, and we don't want hours, we want seconds. So let's get our conversion factor for turning kilometers into meters. Well, we know that there are 1,000 meters per every 1 kilometer, right? Again, a conversion factor is really just a fancy way of writing 1, because this is the same thing as this, just written in a different units. 1,000 meters is the same as 1 kilometer. So since this is really a 1, we're not going to change what this number means. We're just going to change how it's being expressed in terms of units, how it's being measured, okay? And I can tell I did this right because kilometers over kilometers will cancel, and so I'll just be left with meters. And this makes sense, right? If I stopped here, I would have 60,000 meters per hour. Well, that makes sense because a kilometer is 1,000 meters. So 60,000 meters per hour is 60 kilometers per hour. But we're not done because we also want to get rid of these hours. So let's use our conversion factor there. Now I got to be careful, right? Common student mistake would be to do this. But notice, hours won't cancel if I do that. We'll have hours times hours in our denominator, right? Hours and hours would give me hours squared. I don't want that. I want hours to cancel out. So I need to put hours up here so that hours over hours cancels out. And I want to replace those with seconds. So 1 hour is 3,600 seconds, right? Because 60 minutes in each hour and 60 seconds in each of those minutes. So 60 times 60 gives me 3,600. So I'm going to do 60 times 1,000 over 1. and then times 1 over 3,600. In other words, 60 times 1,000 divided by 3,600. And that gives me that this scooter's final velocity in meters per second is 16.666, repeating, I'm just going to do 4 or 5 digits after the decimal, meters per second. Remember, do not over round, okay? We want to carry extra digits with us. It's only our final answer that we're going to round to sig digs. If we keep rounding over and over for every calculation we do, by the time we get to our final answer, we can actually change it so that it's off by a bit. Okay, so we've listed out our givens. What are we actually being asked to find though? Well, the magnitude of the acceleration is blank, right? So we just need to find the magnitude of the acceleration. We don't need to find its direction, okay? But we wouldn't really be able to do that anyway here because it didn't tell us what direction it was going. So we've done givens. Now we just got to say, okay, what are we trying to find? We're trying to find the acceleration. So I usually show that like that. I want to find acceleration. Acceleration equals question mark. So I know it might seem a bit tedious to rewrite all of this information, but the reason that's going to be super helpful is that we are seriously now more than half the battle is already won, okay? Because now all we need to do, we can see what information we have and what information we want, right? We have T, VI, and VF, and we want A. So all we need to do is go to our formula sheet and find the formula that has all of that information in it and nothing else, right? So we'll go to our formula sheet, we'll take a look at our kinematics section up here, and for example, we can see, oh, this one's no good because it has displacement, right? I know we haven't learned these yet, but eventually you have to know which equation to choose. I'm not going to tell you which equation to use, right? These all have displacement, so that won't work because we don't know displacement. We also don't care about finding displacement. However, this one, we know it has the acceleration. Well, that's good because that's what we want to find. It has the final and initial velocity. Good, we know those. And the time. Good, we know that. So that equation will work. We've now selected our formula. So see how much writing out this list just kind of simplifies the problem, right? We had all of this information to kind of sort through, right? But now we just have this nice quick little reference to say, okay, what do I know? What do I want to know? What equation is going to let me work with that? Okay, so we write down our equation from the formula sheet. Next, we would check if we need to manipulate it, but we actually don't in this case. Life's good. We want to find acceleration. Acceleration's already isolated. So we're actually ready now to just go and plug in our numbers. And this is the other reason this little list is nice. Right now, instead of having to go back to the question and find the final velocity, I've just got it listed out here. I've already converted my units. I'm ready to just plug in. So let's go ahead and do that. The acceleration is going to equal the final velocity, so 16.6 repeating meters per second, minus the initial velocity, so 0 meters per second, divided by the time, so that is 6.13 seconds. So now we take out our calculator, we put that in, we'll do forward order of operations. So first I need to do this, but 16.6667 minus 0 is still just 16.6667. So divide that by 6.13, and I'm getting that the acceleration is 2.7189 meters per second squared, right? Now always, again, keep your unrounded answer because you might need it later for step 2 or something, okay? But in this case, for this part anyway, this is our final answer. So now we just do all our checks, right? Do we have our units? Yes. Is this the appropriate number of sig digs? It's not, right? So we go back and we see, okay, what's the least number of significant digits in any of the data I used? From rest, it's 0 meters per second. That almost has infinite sig digs because it really is just 0.000000, right? But this has 3 significant digits. This has 3 significant digits. So it looks like our answer should have 3 significant digits. So 2.7, and then I need to decide if this stays as a 1 or goes to a 2. Well, it's followed by an 8, so we would round that up to 2. So 2.72 meters per second squared would be our final answer, okay? For this numerical response format, how would we fill that out? We would do 2.72. So the decimal gets a box, okay? 2.72, like that. All right, let's try this next one. So a ball is rolled up a hill with a velocity of 10 meters per second. After 45 seconds, the ball is rolling down the hill at 5 meters per second. Okay, let's just quickly draw a diagram to get our bearings here. Okay, make sure we're not missing anything. So the ball is rolled up the hill initially with a velocity of 10 meters per second. Now, after 45 seconds, the ball is rolling down the hill. So we got to be very careful here, right? See how sometimes a diagram can help? Because afterwards, our velocity is downhill at 5 meters per second. So right away, as we always should, right? I'm going to define my directions because I'm dealing with opposites here. So very important to keep track of what's in opposite directions. I'm going to call uphill positive and downhill negative, which means my final velocity is, since it's downhill, it's not 5, it's -5 meters per second. Okay, so always be careful there. You need to be on the lookout for things being in opposite directions. A picture can help a lot with that. Okay, you will get the wrong answer if you put in +5 for this question. So let's write out our givens. We're given that the time is 45 seconds. And then the initial velocity is 10 meters per second uphill, and the final velocity is 5 meters per second downhill, which I'm going to represent with a negative. Okay, the magnitude of the acceleration in scientific notation is a point BC times 10 to the negative d. Okay, so we'll talk about how to fill out our answer there, but we can see that we are looking for acceleration. Okay, so again, you won't be told which formula to use. You've got to figure it out. I know right now it's obvious because we've only talked about one formula, but eventually you're just going to have to pick out which formula is helpful based on the information you have and want to know. So once again, we would go to our formula sheet. Okay, we're ready to do that because we don't have any kilometers or hours. Everything's in standard units. But it looks like, once again, this formula will be the one we want. Okay, so once again, life's good. We don't need to manipulate this, right? It's already solved for what we want. So we're ready to just plug in our numbers. Luckily, we have a nice little list here where we can just take VF and put it right in there, right? VI, time, and that gives us this equation after plugging everything in. So see what I mean? If we had missed that they were in opposite directions, we're about to get the wrong answer then, right? Because 5 minus 10 is not the same as -5 minus 10, okay? So we get that doing -5 minus 10 divided by 45. I'm getting that the acceleration is negative 0.33333 meters per second squared. Okay, so we got our, answer. Now we just do, our checks, right? Do we have sig digs? Do we have units? All that kind of stuff. Now, part of that too is making sure you're answering in the format the question asked for. So you might be looking at this and saying we should only have 2 significant digits. You would be correct. However, when they tell us to give our answer to 3 sig digs like they're doing here, we just listen to them. So we'll give it to 3 significant digits, okay? Usually those match, but sometimes they'll ask you for a different number than you technically should have. So let's just, to 3 significant digits, this would be 0.333 meters per second squared. Notice I dropped the negative because I need to interpret what that negative means in terms of direction. So what did a negative mean for us? It meant downhill, right? This thing is accelerating downhill, right? That's why it was going up. It eventually got slower and slower and slower, stopped, and now it continues to accelerate downhill, so it'll get faster and faster down. Okay, now to express this answer in the format they need, we're still not quite there. We need to write it in scientific notation and then tell them what A, B, C, and D actually are. So remember, for scientific notation, we always need a number between 1 and less than 10, right? Times 10 to the power of something. So right now we have 0.3. We need to move this decimal, okay? So we're going to move it here to give us 3.33. So our acceleration is 3.33 times 10 to the power of, and how many places we moved the decimal will be the exponent, okay? We only moved it once, but remember, this is going to be times 10 to the power of -1, because this indicates that we are really taking 3.33 and dividing it by 10 once to get what our answer is, right? That's 10 to the -1 means divide by 10 once, okay? So there would be our answer. And so to actually record this in, Smarter Marks or on a Scantron sheet, notice what it's now saying. It's saying our answer should look like a point BC times 10 to the negative D. What are the values of A, B, C, and D? So that just means write it out so that it looks like this, and then tell us what numbers go in that spot. So you can see A point BC times 10 to the negative D, right? And we just look, so A is 3, B is 3, C is 3, and D would be 1, right? Not negative 1, they already put the negative in for us, right? So A, B, C, and D are just 3, 3, 3, and 1. That's how we would record a numeric response in this format. So now that we've done some together, time to pause the video and try one out on your own. Okay, so no matter what, go ahead and try this one out. You can check your answer against that one there or in my solutions. Okay, if you're wanting a little more practice with this before moving on, these are also good ones from your assignment that you can try. Okay, and then you don't have to do them again later. Or you can also save those until you're doing the rest of the practice later. But at the very least, pause the video now and do this one for sure. Okay, and then we'll move on to another kinematics formula. All right, and here we are. This is officially the first thing you are learning for the first time in Physics 20. This is the first thing we've seen that you did not see in Science 10. I know it might have been a while and some recap was necessary, but we've officially now entered into new stuff, okay? So here is our second kinematics equation, okay? Now again, they're all useful when there's one variable you know or don't want to know. 5 variables, so that gives us 5 equations. So this one is useful when you don't know and you don't want to know the, give you a second, yeah, the acceleration, right? Because acceleration doesn't appear, so that's a good thing if you don't know it, right? But it also won't help you find it if that is what you wanted to find, okay? Again, just a reminder here, V equals D over T or D equals VT only works when the acceleration is 0, okay? So whenever we have non-uniform motion, we need to be thinking about these 5 kinematics equations, not a V equals D over T. All right, let's get some practice manipulating this one. So starting from how the equation appears on our formula sheet, right? This is how it looks on our formula sheet right there, okay? We want to now isolate VF. Because remember, all you get is your formula sheet for quizzes and exams, right? So you need to be comfortable with manipulating to find the variable you need, not just the one that's already isolated on your formula sheet. Okay, so always the same process. We want to find final velocity. Right now, it is not isolated because there are lots of operations being performed on it, right? It's being added to VI, it's then being divided by 2, and it's being multiplied by time. So we're going to undo those operations one at a time until final velocity is by itself, but we have to remember reverse order of operations. So there's a lot going on in this brackets, but before I'm even allowed in the brackets, I need to deal with everything outside of the brackets. So what is happening outside of the brackets? Well, our velocity is being multiplied by time. What's the opposite of multiplying by time? Right, it's dividing by time. So I'm going to divide this whole side by time. Time cancels out. And I'll write down what I've left with, and things will look a little bit simpler. That's one thing I sometimes find with students is they're a little scared to just get started, right? We're not going to do these all in one step. You're never going to be able to just do it all right away, right off the bat, at least at the beginning, okay? So just do one thing, right? Write down what you're left with, and things will look a little bit simpler. We'll be a little bit closer, right? So all I've done is divide both sides by time, and yeah, I'm a little bit closer. So I regroup, I take a breath, and I ask myself, okay, what's next? I still want to find velocity, okay? It's being added, it's being divided. I've dealt with everything outside of those brackets, which means now I've kind of unlocked the brackets and I'm ready to go to work inside, okay? So I restart. Now, remember, everything here is being divided by 2, so there are implied brackets there, right? So before I deal with the addition of VI, I'm going to need to deal with that division of 2, okay? So to undo dividing by 2, I can multiply by 2. And I take a breath, I write down what I'm left with, and we'll be a little bit closer. So there we go, 2D over T equals VF plus VI. I've dealt with everything outside of those implied brackets. I ask myself the same questions all over again. I want to solve for final velocity. It's not by itself because we're adding the initial velocity. That's the last operation we have to undo. So the opposite of adding initial velocity is subtracting initial velocity. So plus VI and minus VI just cancel each other out. Now on this left side here, here's a common student mistake I see. Okay, this is wrong. Do not write this. They do this, right? They put the VI in there. But we had this left side, 2D over T, and we subtracted VI from that whole thing, right? Notice now we're only subtracting VI from 2D, and then for some reason, VI is getting divided by T, right? How did that happen? So whenever manipulating, remember, you're just doing operations, right? Ask yourself, okay, what am I doing here? Well, I'm subtracting VI from 2D over T. So 2D over T minus VI, right, will be our final velocity. If we had ended up dividing VI by time, we would know something went wrong because we're not just writing, scribbles out, we're performing operations. So there's no way for VI to end up divided by time there, right? That would clue us in that something had gone wrong. And again, it's usually common practice to write the isolated variable on the left side. So I'm just gonna rewrite it with VF isolated on the left. And there we go, we did it. Okay, let's now do VI. It's going to be very similar to VF. So I would actually suggest that you maybe pause the video. And since we've just done a very similar one, see if you can solve for VI on your own. And then you can press play and see how it goes. That goes for any time in the video lesson, really. You can always pause, try the next step on your own, and then press play to see how we compare. Okay, so let's go ahead and give this one a shot. I'm going to do the same process. I'm going to go a bit quicker here. I want to solve for VI. So I ask myself what operations are being performed on it, remembering the reverse order of operations. So first things first, everything in the brackets is being multiplied by time. Let's divide by time. That's going to leave me with this. Okay, now everything here is being divided by 2. To undo that, I need to multiply by 2. That's going to get rid of the 2 here and multiply this side by 2, and I'm left with just VF plus VI. I want to solve for VI. Right now, it is having VF added to it. So to undo that, I can subtract VF from both sides. And now all that's left on the right side, we did it, right? We undid all of the operations that were being performed to VI until it's the only thing on one side of the equation, and we've isolated it. All right, last one here, we want to solve for time. Okay, well, we ask ourselves, this is one I find students sometimes overcomplicate, right? Remember the core question. We want to solve for time. Right now, time is not by itself because an operation is being performed on it. So what operation is being performed on time? It's actually just one operation. Time is being multiplied by this stuff. So what's the opposite of multiplying by this stuff? Dividing by this stuff, right? So we can just say, if time is being multiplied by that, well, to undo that, I can just divide everything, right? It might not look super pretty, and we can do some simplification in a second here, okay? But that's totally valid. Time is being multiplied by this, so if we divide both sides by that anything over itself is 1. So let's just rewrite this and then think about some simplification. Okay, as is, this does work. Like, this will give us the right answer. However, it's a little bit, messy, and it gives us a lot of chances to actually mess up on our calculator because there's fractions within fractions here. So this would totally work. This will give you the right answer, nothing wrong with it. But personally, I would like to simplify this a bit. And probably the easiest way to do that is, remember, dividing by a fraction is the same as multiplying by that fraction's reciprocal, right? For example, dividing by 2 is the same as multiplying by 1 over 2, right? Recognizing that 2 could be written as 2 over 1, right? For a more fraction-y example, x divided by 3/4 is the same as 4/3 times x, right? Dividing by a fraction is the same as multiplying by that fraction's reciprocal, the flipped fraction. So applying that here, dividing by VF plus VI over 2 is actually the same thing as multiplying by 2 over VF plus VI. like that, right? So dividing displacement by this is the same as multiplying displacement by the flipped version of the fraction. And even that, I mean, again, we are good here. We were even good back here, okay? But I could simplify this a bit more. This is d over 1, so I could clean it up a little bit and say this. And then that's just a little bit nicer to look at, and B, a little bit easier to enter into our calculator when the time comes. Okay, so we've met a new formula, we've manipulated it, looked for every variable that it contains, okay, isolated them all. Let's actually go ahead and apply this now with an example. Okay, so a policewoman investigates a car accident. This is a real job, by the way, too. You can be a forensic physicist, analyze, motion that must have occurred, okay, to come up with what events might have transpired. Anyway, the tire skid marks are 22 meters long. An eyewitness states that the car skidded for 3.5 seconds. If the speed limit is 50 kilometers per hour, will a speeding ticket be issued? Okay, so sometimes, if students come to physics with a conception of, it's just putting numbers in formulas, right? I mean, that's part of it for sure, but a lot of physics is interpreting what's going on, right? Being able to pull out the necessary information and then analyzing that situation. So this is one definitely where I think a diagram is going to be really helpful, right? To first figure out what is even going on here, right? What exactly are these numbers related to? How do they tell us about the scenario? So if the tire skid marks are 22 meters long, okay, well, that's telling us about a displacement that was traveled, okay? Now, if the skid marks are 22 meters long, it was traveling that far, so it was moving initially and it, got in an accident, so at the end, well, we can read between the lines a little bit here, right? Sometimes it's not going to explicitly tell you something, but how fast would the car be moving after skidding, right? It's the collision happened, they're skidding, and then they stop, right? They must have stopped. So our final velocity, we know, is 0 meters per second, okay? Now, we also know from the eyewitness that it skidded for 3.5 seconds. Now, it's asking us if this is the speed limit, will they get a speeding ticket? So what do we need to find in order to answer that question? Right, we need to know how fast were they moving before this collision and then the skidding that brought them to a stop, right? I should probably just make that a one-sided arrow. There we go, okay? So a little bit of a diagram here helps us kind of sort this information out and think about what it's telling us. So now let's make our list of givens and required, and then we can select an equation in order for it to analyze this. Okay, so here's everything we were given. We need to find the initial velocity, and I just made a note for myself here that yes, we do need to find the initial velocity, but that's not just going to be our final answer, right? Our final answer is, will they get a speeding ticket? So we're going to find that, and then we're going to compare it to 50 kilometers per hour. So the nice thing about writing out this list is now we have a nice, clear little checklist of what we want to be in our equation and what we don't want to be in our equation. So notice here, we can see right off the bat, we don't have acceleration. We don't want to know acceleration, and we don't know acceleration. So that kind of gives us a heads up of what we're looking for in a kinematics equation, right? And we can see, okay, definitely not this one, that has acceleration. Not this one either, that has acceleration, right? Not this one either, that has acceleration. But this one, hey, we have displacement, we have the final velocity, we want to know the initial velocity, and we know the time. So that equation will work pretty well. Let's write it down and see if we need to do any manipulations. Okay, so in this case, I am going to need to manipulate it because I want to find the initial velocity. Right now, that is not by itself. Okay, so it is okay to notice things like, if we want to make our lives a bit easier, we can notice that, well, hey, our final velocity is just 0. So if we want, we can just take that out right now, right? 0 plus VI is still just going to be VI. Not mandatory, but we can definitely, it's okay to notice things like that as long as you show me with something like that so that I don't think you just forgot the final velocity. Okay, so now that leaves us with just this situation. Still though, we need to find initial velocity. It's being divided by 2, it's being multiplied by time. Let's undo the multiplication by time by dividing both sides by time. That leaves me with this. So we ask ourselves the same question. VI right now is being divided by 2. So to undo that, we can multiply by 2. And there we go. We did it. We isolated the initial velocity. So let's go ahead and plug in our numbers. So we need to do 2 times the displacement. So 2 times 22 meters divided by the time. So 3.5 seconds. So now I just need to put into my calculator. I need to do 2 times 22 and then divide that by 3.5. And when I did that, I got that our initial velocity is 12.5714 meters per second. Now, okay, pause, right? That is the number we needed to find, but we haven't actually answered the question. So always a good idea, go back, double check that you've actually done what the question asked. And we did need to find this, but it's actually not our final answer. We now need to compare this to 50 kilometers per hour, which means we have a problem here. This is in meters per second. This is in kilometers per hour, so we can't directly compare them, right? We've got to convert either this to meters per second or this to kilometers per hour. I'll probably go ahead and convert this to kilometers per hour. So let's now remind ourselves of how to do that, okay? But again, just need conversion factors. So we need meters to become kilometers, and we want our meters to cancel out. We know that 1 kilometer is 1,000 meters, so we're going to divide by 1,000. That makes sense because 1 meter is only 1/1000th of a kilometer, so we should be getting a smaller number after doing that conversion. But then we don't want to know how many kilometers it went in just 1 second. We want to know how many kilometers it went in a full hour. Okay, so we need to multiply by how many seconds there are in an hour. And again, we can double check that we did that right because we'll have seconds over seconds canceling out there. And there are 3,600 seconds in 1 hour. So again, makes sense. We'll multiply by 3,600 because we want to know how far it would have gone in a full hour, not just 1 second. Okay, so that gave me that the vehicle must have been traveling then at 45.2 kilometers per hour. So since the speed limit was 50 kilometers per hour, they would have been going under the speed limit, right? So think about what we just did, right? It's pretty cool. Based on how far they went, the speed they ended up with, and how long it took them, we can work back to how fast they must have initially been moving. And so in this case, we can declare that no, they were not speeding when the collision occurred, and so no speeding ticket will be issued. So there we go. There is our final answer with our justification. Okay, so now pause the video. For sure do this one. Okay, go ahead and try this one. I always put it in directly in, so you don't have to go flip open the textbook if you don't have it on hand. Okay, compare to your answer there. And then again, if you're wanting, maybe you think, I'd like to try one more with this formula or a couple more. These are some good ones that make use of that formula, okay? Or again, you can wait and do those extra ones afterwards with the rest of the assigned problems, okay? But at the very least, pause and do this one from your assigned practice problems now before continuing. All right, next kinematics equation. Go ahead. You tell me which variable goes here. This is useful when we don't know and don't want to know the final velocity. Just a little side note for this one. This one's often very helpful when something is dropped. And the reason is that we already know that the acceleration and the initial velocity whenever something's dropped, right? The acceleration will be 9.81 meters per second squared down because that's acceleration due to gravity on Earth. And the initial velocity will be 0 because it wasn't moving yet when it was dropped. And that makes this even nicer because then that whole term goes away. So obviously it's not the only thing that you can do with something being dropped, and there's other things you might sometimes think about. It's not the only thing you can analyze with this equation. I just wanted to point out, often when something is dropped, this one will be quite helpful. Okay, so now it wants us, you know the drill here. We're going to get lots of practice with isolating variables. Let's go ahead and solve for each variable in this equation, right? Because all we have is our formula sheet. We have to have the skill of being able to take that and turn it into an equation for whatever it is we want to find, okay? Quick note before we do that. I will never give you a problem where you need to solve for time using this equation if the initial velocity is not 0. Okay, and the reason for that is that time shows up twice in the equation, which just means you would need to learn the quadratic formula, which you will learn or maybe have already learned in Math 20. But because you don't have to take Math 20 to take Physics 20, I can't assume you know it, okay? So you might use this equation to solve for time, but in those cases, the initial velocity would have to be 0. Okay, so when we go to isolate for time, we're going to assume the initial velocity is 0. You can't just assume that, but you will encounter situations where you know the initial velocity is 0. Like, for example, when something is dropped. Okay, let's go ahead and write down the equation from our formula sheet and then solve it for initial velocity. Another note on this one too, sometimes students, this is how it's written on your formula sheet. I find most students, and honestly, I myself kind of included, find it a little bit easier to work with. Instead of writing it as 1/2 times AT squared, just doing AT squared divided by 2, right? We know that's the same thing as multiplying by 1/2. And for whatever reason, I find it just makes it a little easier to work with. Whatever your preference is. You could even do the 1/2 as 0.5 if you prefer that, okay? So I'll write it this way typically. Don't get thrown off by that. You can also do the 1/2 or the 0.5, whatever floats your boat. But let's go to work here solving for VI, okay? So it is not isolated, right? Why is it not isolated? Well, because it's being multiplied by t, and we're adding AT squared over 2. Okay, so which one of those things do I need to deal with first? The addition or the multiplication? Right, reverse order of operation tells us before we can deal with the division, we need to deal with the fact that we're adding AT squared over 2. So the opposite of adding AT squared over 2 is subtracting AT squared over 2. If I do that to both sides, I am left with this. Okay, and repeat that process. We want to solve for VI. It's not isolated because it's being multiplied by time. What's the opposite of multiplying by time? Right, divide by time. And that leaves us with this, okay? Now again, this is good enough. This will actually do the trick, right? We could probably simplify it a bit and clean it up a little bit. One way we could maybe do that is to recognize that dividing by time is the same as multiplying by 1/time, and that might make it a little easier to look at. But honestly, this is fine. This will do the trick. If I did want to simplify it a bit, I would probably go like this. I would split it up. I'm dividing both terms by time, so I can do displacement over time minus AT squared over 2 divided by time, and then rewrite that division by time as multiplication by 1/time. Like this here, so that I don't have a fraction within a fraction, right? And then we can see that, hey, t squared divided by time, well, time squared is just time times time, right? Time times time. So if I have time times time divided by time, I can just get rid of that squared, leaving me with a slightly simplified version, something like that. All right, you can decide if it's worth it to you to simplify it or not. Honestly, this will work just fine. There's nothing wrong with writing it either of those ways, okay? All right, let's solve for the acceleration now. So there's a whole bunch of operations being performed on the acceleration. It's being multiplied by time squared, it's being divided by 2, and it's having VIT added to it. So reverse order of operations, right? Deb. So first I need to deal with that addition. So I'm going to subtract VIT from both sides. That's going to give me this, and then I pause, I take a breath, things will look a little bit simpler, right? I've gotten rid of VIT, and now I ask myself, okay, it's still not by itself, it's being multiplied by time squared, it's being divided by 2, let's go ahead and multiply both sides by 2 to cancel out that division by 2, and be very careful here, common student mistake would be to just do that, right? 2D, okay? But we multiplied this whole side by 2, we have to multiply this whole side by 2. So I'm going to make sure everything gets multiplied by 2. Okay, I write down what I've got, I take a breath, and then I take the next step. I ask myself once again, okay, why is acceleration not isolated? Because it's being multiplied by time squared. The opposite of multiplying by time squared is dividing by time squared. And that leaves us here, okay? Now, honestly, any simplifications we could do here, honestly, don't get it much simpler. So I would probably just call it a day there, right? That'll work just fine. We can put in all of our variables and solve for the acceleration, right? So same process. one at a time, undo the operations that are being performed on the variable you want to isolate, following that reverse order of operations. Bed mass backwards. Okay, last one, we're now going to solve for time. Again, in Physics 20, if we have to use this equation to solve for time, the initial velocity will be 0. Or rather, if we can use this equation to solve for time, that only works when the initial velocity is 0. Okay, so it doesn't mean we can just assume the initial velocity is 0. We have to actually see that in the question, okay? But this is not solvable for time until you've learned the quadratic equation, unless the initial velocity is 0. So that means we're going to have just this, okay? And we are solving for time. So what's happening to time? Well, it's being squared, it's being multiplied by the acceleration, and it's being divided by 2. So what do I deal with first, the squaring or the multiplication and division? Right, before I can deal with that squaring, before I can undo that, I have to undo the multiplication and division. Reverse order of operations. Okay, now that we've done a few of these, I'm going to step it up a bit here. I'm going to show you something, okay? Multiplication and division are really together, right? So we can kind of deal with them at the same time if it's convenient and if we feel like it. We don't have to do this. It is being multiplied by acceleration. It is being divided by 2. So if we want, we can multiply by 2 to cancel that out and divide by the acceleration, okay? We could do this as 2 separate steps. Don't freak out, okay? But just showing you some, some next level kind of thinking about it to save ourselves some paper as we write, okay? So we could do that, okay? That would leave us with 2d over a equals t squared. Notice if I had broken it up into 2 steps, I'd be in the same place. I'd multiply both sides by 2 to get 2d, and then I'd divide both sides by a to get 2d over a, okay? Whatever you prefer, up to you. Just wanted to show you that sometimes you can, if you're dealing with divisions and multiplications at the same time, they're together in the order of operations, so you can do that. Okay, now, here we are, almost there, but we haven't solved for time. We've solved for time squared, right? We don't want to know what t squared is, we want to know what t is. So, what operation's being performed on t? It's being squared. What is the opposite of squaring? It is square rooting. So I will square root this side and I will square root this side. We find that time is equal to the square root of 2 times the displacement divided by the acceleration. Okay, that is all being square rooted. And there we go. We're ready to take this equation for a spin with some real examples. All right. So a curious student drops. That's very important because right away we know a few things, okay? We know its initial velocity is 0, and we know its acceleration is 9.81 meters per second squared downward. But let's keep reading here. Drops a bowling ball down an 8-meter deep well. The time it takes to reach the bottom of the well is blank seconds. So again, a diagram might be helpful here, okay? We're going to draw our well and our bowling ball, and let's just add in the information we know, okay? We know that the well is 8 meters deep, and we want to know how long it takes to reach the bottom, right? So what does that tell us? Well, that tells us it's going to have to travel 8 meters downwards, okay? I'm going to go ahead and call downwards negative. That's the most common. Again, we just need to make sure opposite directions have opposite signs, but most common would be to call down negative. So I'm going to say 8.0 meters down, and then when I go to put in the numbers in my formula, I'll make that negative, okay? Now, if they drop the bowling ball, again, at first it's not moving, right? It's about to because gravity will accelerate it downwards, but the initial velocity is 0 meters per second. And as soon as that student lets go of the ball, right, it's going to start accelerating down at 9.81 meters per second each second. Okay, let's go ahead and write out our givens. So notice here, right, like I said, they're not always just going to necessarily tell you here is the acceleration, here is the initial velocity. We have to interpret the situation sometimes. But since it was dropped, we're able to figure out that the initial velocity is 0. And since it was dropped, we know that the acceleration is 9.81 meters per second squared downwards. And we are being asked to find the time it will take. So as always, right, we have what we were given and what we need to find. So we'll go to our formula sheet and we'll figure out which equation works. Again, I know it's a little obvious right now because we just learned the equation, but no one's going to say, hey, use this equation. You've got to figure that out. Okay, well, this one's no good because we don't have the final velocity. We don't care about it. Hey, we know the displacement. We know the initial velocity is 0. We want to know the time, right? And we have the acceleration because it's acceleration due to gravity on Earth. Okay, those ones won't work. We don't know the final velocity and we don't want to know the final velocity. So there's our equation. All right. Now we do need to isolate for time here, okay? But that's actually not going to be possible until we learn the quadratic formula because we have a time and a time squared. So we'll never just get time by itself on one side. However, in the case where the initial velocity is 0, this formula can work because if the initial velocity is 0, then this whole term is 0. And so that just leaves us with displacement is equal to AT squared over 2. We want to solve for time, so it's being squared, multiplied by acceleration, and divided by 2. Let's go ahead and multiply by 2 to cancel that out. And while I'm at it, I'll divide by acceleration to cancel that out. That leaves me with this. Time is being squared. To undo that, I can square root both sides. There we go, we did it. We're now ready to plug in and solve for the time. So the square root of 2 times d, so 2 times negative 8 meters, divided by, our acceleration is also downward, so negative 9.81 meters per second squared, right? Your palms might have started to sweat a little bit when you had a negative in a square root because you know you can't take the square root of a negative, but it's okay because we have a negative over a negative, so those go away, okay? So I would definitely recommend breaking this up into chunks on your calculator instead of trying to put it all in one big step. Don't be scared to, break it down a bit. So maybe first do 2 times negative 8, divide that by negative 9.81, and then press enter. And then you've got what you need to take the square root of, right? So I might do that. So this is the result of just doing everything inside the square root. Just want to take a second to talk units here too, right? We can see, we've got meters over meters, so those will cancel out. We're left with 1 over seconds squared. Like this, right? Well, we know that dividing by a fraction, dividing by 1 over seconds squared is the same as multiplying by its reciprocal, so seconds squared over 1, right? Which is just seconds squared. So that's a good sign because look, right now, my units inside the square root are seconds squared, and I'm about to take the square root. So I'm going to be left with seconds, which is the unit of time. So all these nice little ways we can check our work as we go. So now taking the square root of that number, I got 1.2771 seconds. Okay, almost done. Got our raw answer, but now we do our checks, right? Things like units. Do I have the correct units? Yes, we want time. It's in seconds, and the question asked for seconds. Sig digs. I need only 2 significant digits, right? I did use that number, so I'm going to have to round this instead of 1.2771. 1.3 seconds. 2 gets rounded up to a 3 because it's followed by a 7. Okay. And direction, well, it's time. It's a scalar. So I don't need a direction here. I couldn't give one even if I wanted to. Okay. So now to fill in our answer, 1.3. So in the first box, we put a 1, second box decimal, and then a 3. And there we go. We found the time. So right around this time, I get a question from students like, well, hang on a sec. What if we drop something different? So a second student drops a feather down the same well. How long does it take to fall? So, let's think about it. We have the equation here essentially for finding how long it will take to fall, right? Let's think about what's different. If we drop a feather, its initial velocity is still 0. We're dropping it, so its acceleration is still 9.81, right? And it's the same well, so it has to travel the same distance. So all of the variables are the same, right? So, again, the numbers don't lie. It should be the same. This leads us to a common misconception and also an important assumption that we are making here, okay? So you'll see there, we calculated the time to fall without using the mass of the object. At no point did we have to know how big the bowling ball was to make this calculation. So we can see that mass should make no difference to how long it takes to fall. And it doesn't, with an important thing to note here, okay? I mean, again, it makes sense. Acceleration due to gravity is just 9.81 meters per second squared. No matter what kind of object is falling, that's the acceleration due to gravity, right? But we all know that in reality, the bowling ball and the feather would take different amounts of time, right? The feather would kind of flutter back and forth, whereas the bowling ball would just fall, right? That's because we're ignoring something here. Okay, so objects will accelerate downward at the same rate and therefore take the same amount of time to fall if there is no air to displace. So for example, in a vacuum or on the moon, okay, I'm going to link a video in the description that you can go watch and see that I'm not lying. This is true. A feather and a bowling ball really do take the exact same amount of time to fall as long as there's no air. And the reason behind that is that air resistance is an upwards force. We're going to talk lots about forces in Unit B. And what forces do is they change accelerations. So air resistance works against the downwards force of gravity and therefore changes the acceleration. Okay, so when there's air resistance, the acceleration might not exactly be 9.81. We're going to study this relationship between the total force acting on an object and its acceleration a lot in Unit B. So in air, all objects will essentially fall at the same rate if they have the same shape. You can try this out yourself. Get 2 water bottles, have one be full and have one be empty, close the lids and drop them. You'll find that they do hit the ground at the same time. And that's because they have the same shape even though they have a different mass. Because it's actually your shape that determines how much air resistance you experience. You can try this out yourself next time you're driving carefully, right? Stick your hand out the window and try turning it sideways so that there's a big surface area exposed, right? And then turn it facing down so that there's just a small area exposed. And you'll notice you feel a very different force from the air that your car is moving through. So, all that being said, we are usually going to ignore air resistance. That is why in this problem, right, we're seeing that the bowling ball, we didn't worry about its shape, we didn't worry about its mass, okay? Most of the time, that's actually a fairly safe thing to do. It makes a slight difference, but a lot of the time it is pretty much negligible, like the bowling ball. But sometimes it can be quite significant, like in the case of a feather, because a feather has a wide surface area and a very small mass. That air resistance actually does make a big difference to the acceleration it experiences. Okay, so that's kind of a little, a note to be aware of the assumptions we're making, and also a look ahead to how we're going to study that relationship between force and acceleration in Unit B. Okay, so now pause the video lesson, go try this one, okay? Check your work against the answer, and then as always, if you want to get a little more practice with this formula before moving on, you can try these, or you can save them for the end when you sit down to do the rest of the practice problems. Okay. 3 equations down, 2 to go. So this one is very similar to the one we just looked at with a slight difference, okay? Instead of the initial velocity appearing, the final velocity appears and there's no initial velocity, which tells us we can use this when we don't know and don't care about that's right, the initial velocity. This one is often really helpful when we know an object comes to a stop, but we don't necessarily know how fast it was going to start with, right? Because then VF is just 0. So that's sometimes when this one is used. Not the only time, of course, but one helpful application. Okay, we're not going to do the manipulating for every formula, for every variable here. You can if you want. It's so similar to the last one, and it's good to get your practice on your own with it as well. So let's just jump straight into an example. So we're told that a moose runs onto the road 35 meters in front of a moving car. The car slows at a rate of 5 meters per second squared for exactly 4.5 seconds. Did the car hit the moose or did it stop in time? Okay, so we got to think here a bit, right? I think a picture will be very helpful. So we got a car And then we got a moose. Again, doesn't need to be a work of art like mine is, okay? Just something to, help you get your bearings. A scared moose. Okay, now the moose is 35 meters in front of the moving car. So we know that that's the distance the car has to stop within to not hit the moose, okay? Now careful, we don't actually know that that's how far the car went, right? We are actually trying to figure out, I would say one way we could approach this is to figure out how far did the car go, right? And then we can compare it to 35 meters. So the car slows at a rate of 5 meters per second squared for exactly 4.5 seconds. Now, very important to note here, right? The car is going slower. So whatever direction we define as positive, what does that mean for this acceleration, right? It needs to be negative. It's accelerating this way, right? Moving forwards, but accelerating backwards in order to slow down, okay? And we know that it did this for exactly 4.5 seconds. Okay, so I'm going to say the displacement's actually what we want to find, and then we'll compare it to 35 meters, okay? Now, we actually do know one more thing, because if it came to a stop, what do we know at the end? Right, we know its final velocity is 0 meters per second. It's going to want to come to a stop, right, in order to avoid hitting the moose. So what we need to figure out is if it came to a stop after accelerating backwards at 5 meters per second squared for 4.5 seconds, how far would it have traveled forward? Okay, so there's our plan. Let's write out our givens and our required. I'm looking for displacement, and I'm going to give myself a little note that we need to then compare that to 35 meters. And then we're given all these variables, right? So notice it's not always just there's a number, I'm going to put it in, right? We do have to use our brains a little bit here and think through what we're actually analyzing. Okay, but same as always, right? We are given 3 variables. We want to know a fourth. That means one of our kinematics equations will work. In this case, we're looking for the one that does not have initial velocity because we don't know initial velocity, but we also don't really care about it, right? And that leads us to this guy here. So let's go ahead and write it down. Again, same thing. I'm going to choose to write 1/2 as over 2 instead, but that's totally up to you, whatever you prefer, okay? And now in this case, life's good. We even know that the final velocity is 0. So if we want, we can go ahead and take it out, right? 0 times time is going to be 0 no matter what time is. Oops, I messed up there. That's actually a common student mistake for this one too, is to not read the formula sheet careful and put a plus, but I just did it myself. It's minus, right? So always, especially at first, be careful that you're not mixing up the operations there. Okay. And then don't forget, we still have that minus, right? 0 minus this is going to be negative this. So don't drop that negative. All right, but we're ready to put in our numbers. Life's good. We don't even have to manipulate because it's already solved for displacement, and that's what we want to find. So I'm calling the direction of the acceleration negative. So I'm going to put in negative there. My time is 4.5 seconds squared, and we're dividing that by 2. Now remember order of operations here, right? Now we're doing the operation. So first I'll square this, right? Bed mass, exponents first. Then we can multiply, and then we can divide. So I wouldn't do it all at once. Break it up into little steps on your calculator. But carefully entering that, I got positive 50.625 meters. Now pause and always think, right? Little ways you can check your work as you go. Were we expecting a positive displacement here? Well, yeah, we actually were, right? Because we defined the acceleration direction as negative because it was slowing down, right? Which means we were defining the direction it was moving initially as positive, because to slow down, you would need to have either a positive velocity and a negative acceleration or vice versa. So by saying this, we are saying that the initial velocity we're calling positive so that it can slow down. Now, if it was moving forwards, well then it should have gone through a forwards displacement, right? So this is a good sign that we got a positive there. If we got a negative, we would know somewhere we did something wrong. Okay. Now, that is not the question we were asked though, right? Not just how far did it go. We were asked, did the car hit the moose? Well, the moose was only 35 meters away, right? Our car, in order to come to a stop, if that was its acceleration and it took that long to stop, our car would have traveled 50 meters. So did the car hit the moose? Yes, it hit the moose. It actually really wasn't even that close, okay? So since the car did not stop within those 35 meters, it does hit the moose. Poor moose. All right. All right, for our fifth and final kinematics equation, okay, we have this guy here, VF squared equals VI squared plus 2 times AD, okay? So which of our kinematics variables doesn't appear here? Time, right? So this one can be used if we don't know and we don't care about how long this motion was happening. Let's go ahead and isolate each variable. So writing it down as it appears on our formula sheet, okay, we'll go ahead and first up, solve for final velocity. Well, that's actually not going to be too bad, like always, right? Find the variable we want to isolate, ask what operation's being performed to it to stop it from being isolated, and in this case, it's actually just that it's being squared. We don't want it squared, we just want the final velocity. So the opposite of squaring is square rooting, and that will leave us with the final velocity is equal to the square root of VI squared plus 2AD. Now, very common student mistake here, do not do this, is to say that that square root and that squared cancel out. But they don't, because there's a lot more being square rooted than just VI, right? VI squared, I should say, right? If we were to do that, well, 2AD never got square rooted, and it was supposed to be, right? So we can't do that because everything is being square rooted, right? The best we can do is just leave it like that. But that makes it nice and quick and easy to isolate VF. Okay, now let's isolate VI. So as always, what operations are being performed on VI? Well, it's being squared and it's having this added to it. So we need to undo those, and reverse order of operations says we first need to deal with the addition before we can deal with the exponent. So first, I'm going to undo the plus 2AD. The opposite of plus 2AD is minus 2AD. So I write down what I'm left with, I take a breath, and then I ask myself once again, okay, now what? What operations are being performed to VI? Well, it's just being squared. What's the opposite of squaring? Square rooting. So square root both sides, and we get this. There we go. We've isolated for VI. So subtract the 2AD and then square root. Okay, next up, we want to find the acceleration. Okay, so again, as always, right, what is happening to acceleration? Why is it not isolated? Well, it's being multiplied by 2 and d, and VI squared is being added to it. We know from the reverse order of operations, first we need to deal with that addition. So let's subtract VI squared from both sides. Writing down what we're left with after that, we get VF squared minus VI squared equals 2 times acceleration times displacement. And then, as always, we regroup. We say, okay, I want acceleration. It's being multiplied by 2 and the displacement. We could deal with those one at a time, or we could also just say it's being multiplied by 2, it's being multiplied by displacement. Let's divide by 2, let's divide by displacement, right? That will undo those. 2 over 2 is 1, d over d is 1. And so we get the acceleration will be final velocity squared minus initial velocity squared divided by 2 times the displacement. All right, and finally, let's solve for displacement here. It's actually going to look, you can probably tell, very, very similar to what we just did. So if you haven't been doing it, now would be a good time to try. Pause, see if you can solve for displacement yourself, and then you can press play and see if you get the same result as me. But let's go ahead here. We're going to subtract that VI squared from both sides, and then we are, once again, just going to say, okay, we're a little bit closer. Now d is just being multiplied by acceleration and 2, so let's divide by acceleration and 2. Those cancel out, and we're left with this thing here. Another important note just that I just thought of, Be careful. Sometimes students will take this and rewrite it as this. They think they're simplifying, but it's actually wrong, okay? Squaring and then subtracting is not the same thing as subtracting and then squaring. For example, if I were to do 3 squared minus 2 squared, I would get 9 minus 4, right? Which is 5. But if I were to try and simplify that, quote unquote, to 3 minus 2 squared, I would get 3 minus 2, which is 1. 1 squared is just 1. So be careful. We do have to keep it as final velocity squared minus initial velocity squared. We can't combine them and then square them, which really just boils down to order of operations, right? We have to do exponents before subtraction. We can't just decide to do the subtraction, then the exponent. Okay. All right, and to finish up this lesson, let's take this final kinematics equation for a spin here. So in a police investigation, it was found that a van with new factory tires can come to a stop from 100 kilometers per hour in 45 meters. Okay, so let's just do a quick sketch to get our bearings here. So if it can come to a stop from 100 kilometers per hour, well, that means, initially traveling at 100 kilometers per hour, it can come to a stop. Come to a stop. What does that tell us? Right, it tells us that velocity final is 0 meters per second, right? We know we're going to have to deal with that kilometers per hour, but we can do that in a second here, okay? And it can do that in 45 meters. So I'm going to call... we know it's going to travel 45 meters while coming to a stop, okay? And I just kind of made a decision, so I'm going to stick with it by calling that positive. I'm calling, forward positive then and backward negative, okay? So let's just go ahead and write down our list of givens and what we're actually looking for now that we kind of got our bearings here. Before we go any further, so I don't forget, let's go ahead and convert those kilometers per hour to meters per second. So there are 1,000 meters in every 1 kilometer. So far, so good. Kilometers are canceling out, okay? And then hours, 1 hour contains 3,600 seconds. And we can double check. Hours on bottom, hours on top. Hours over hours is just 1. And this makes sense too, right? Maybe the most important check of all. Does it make sense? Well, if there's 100 kilometers per hour, yeah, multiply it by 1,000 to figure out how many meters you went every hour. But then we don't want to know how far you're going in an hour, just 1 second. So divide by 3,600 because there's 3,600 seconds in an hour. Okay, and that gives me 27.7778 meters per second. That's probably a number you'll memorize by the end of the course, whether you want to or not, just because you do this conversion so often. Okay, all right. And we want to know the acceleration. So a good habit to get into in physics is to make predictions about what you're expecting, okay? To think about, like for example here, we're about to calculate our acceleration. We've defined forwards as positive. So what are we expecting for our acceleration, knowing that it comes to a stop, right? Its velocity is forwards. So its acceleration needs to be backwards to come to a stop. So there's a prediction we can make. We're hoping that we get a negative acceleration since we define the direction of initial travel as positive. Okay, so there's our list of what we're given and what we want to find. Let's go to our formula sheet and see which equation will work here. So we have d, vf, vi, and we want a. Well, again, this won't work because it's got time. This has got time. Time, we don't know time. Aha! The only kinematics equation where we don't need to know time or, care about finding time. So let's go ahead and write that down. And now we just need to solve it for acceleration. Okay, so undo the operations that are happening to it following reverse order of operations. Additions need to be dealt with before multiplication, so I'll subtract vi squared from both sides. Then acceleration is being multiplied by 2 and d, so we'll divide by 2 and d. There we go, we've solved for acceleration. We're ready to put the variables in where they belong. Okay, so our acceleration, v final, well, we know that's just 0 meters per second. the initial, we now know that's 27.7778 meters per second. Don't forget the squared, divided by 2 times our displacement, 45 meters. Okay, just going to move up here where I got some room. Now again, I would absolutely not recommend putting this all into your calculator in one big chunk. Don't be scared to split things up a bit, right? We know we got 0 squared. Okay, well that's just going to be 0. But then we're going to subtract. Don't forget that, right? We're subtracting. And I would probably just square this to get whatever that is. My calculator gave me negative 771.60495. Hey, what would be the units on that? We had meters per second and we squared them, right? We would get meters squared per second squared, right? Okay, and then we're dividing that by 2 times 45, so 90 meters, right? Just breaking it up into smaller pieces so we don't make a calculator mistake. And now we're ready to divide those. And I'm getting that our acceleration is negative 8.5734. Okay, now I want to talk again about units. You can always do this, and honestly, you always should when you have time, right? Do a little unit check and make sure that you're getting the units you should be, right? That lets us know that we did something right. So here I have meters squared per second squared being divided by meters. Meters squared per second squared being divided by meters. Well, we know that's the same thing as meters squared per second squared times 1 over meters, right? And sure enough, meters squared divided by meters just leaves us with meters in the numerator. So we're left with meters per second squared, which is the unit of acceleration. So yet another way we can check our work as we go, right? Doing unit analysis to make sure we're getting what we should be. Okay, so there we go. We got our raw answer, okay? The negative is a good sign, remember, because we defined the initial direction it was moving as positive, and we know it was slowing down. It was braking to a stop. So that is a very good sign. All that's left to do, I think, is significant digits. So 3 sig digs, okay, I wrote 45 here, but it was given to us as 45.0. So our acceleration then, we could say it's 8.57 meters per second squared, and the negative just means backwards. Now the question just asked us for the magnitude of the acceleration. That, remember, just means the size of it. So we do everything the same way we always would. It's just at the end, they don't care about the direction, okay? But we found it anyway. But it would be 8.57. So on Smarter Marks or on a Scantron, we would do 8.57 meters per second squared. And there we go. So that's the process, right? Now, again, you're about to go do your mixed practice. You're going to have to use all different kinds of formulas. You're not going to necessarily be told, use this formula or that formula. And that's why this process is so helpful, right? When you write out what you know and what you're trying to find, you then go to your formula sheet and it lets you, eliminate the ones that aren't going to be helpful and use the one that contains the given information and what you're trying to find. And then it's a matter of just manipulating and making sure you carefully calculate. Okay, so before you go do the rest of your practice, start with this one here, page 52, number 2. Okay, and if you want some more specific practice with this formula, then these ones are a good place to start for that as well. But we are done the notes and examples section of the lesson, so now you're on to go finish the practice anyway. Okay, I know it looks like a lot for this one, but it's, 5 new formulas. Want to give you lots of practice with each one, okay? So try those out. Again, you would not want the first time you try these to be on a quiz or on an exam, the same way you wouldn't want the first time you kick a soccer ball to be during the soccer game, right? It's important to build those skills, get that practice ahead of time, and make sure you're reaching out for help as needed. I'm always happy to support however I can, all right? Okay, done. That wraps up Chapter 1, the first half of Unit A, so you'll now be able to go do your Chapter 1 quiz in Smarter Marks as well, once you've practiced all this stuff and are asked your questions and all that good stuff.